Alright, so in this video we're going to be looking at when and why we would need to write an overloaded assignment operator, a copy constructor, and a destructor in C++. Turns out whenever we write certain classes that have certain types of data members, then we'll need to be writing all three of these. And that's why it's called the rule of three. So in a later video we're going to develop classes in which we write all three of these and show the proper syntax. But for right now we're going to just look at the concepts and the theory behind why we will need these. So let's go ahead and get started. Okay, so what we need to be thinking about is what happens whenever we assign one object to another object, whenever we copy an object to another object, or whenever we delete an object. As it turns out, what C++ provides us by default associated with these operations of assignment, copying, and deleting is often sufficient. But we can have certain classes, depending on their data members, in which these default operations provided by C++ is not sufficient. And that's when we have to do the things that we had mentioned before. We have to write an overloaded assignment operator, we have to write a copy constructor, and we have to write a destructor. So let's first look at an example in which we don't need to write those three. Okay, so let's say that we have a character class, and this is going to be representing characters in a game. So we can go in and instantiate as many characters as we want to in this game, and each character is going to have a name that's of type string, a life of type int, a strength of type int, and an intelligence of type int. So we can imagine creating or instantiating two characters, character C1, which will have a name of Bob, a life of 7, a strength of 5, and an intelligence of 6. And then we'll have another character called C2, or we refer to it as C2. It has a name of Sally, a life of 8, a strength of 6, and an intelligence of 6. So what would happen if we were to do this assignment operation where we assign what we have for C2 to C1? Well, as we see here, we'd end up with the same thing. So C2 had Sally, 8 for life, 6 for strength, and 6 for intelligence. And we can see over here now for C1, after this assignment operation, that we would have for C1 the name of Sally, life of 8, strength of 6, and intelligence of 6. So all the data members got copied over here are assigned to character C1. And this is what we get by default in C++, so we don't have to do anything extra. And this is pretty cool. So let's take a look at another example. So in this example here, we have the exact same data members, but we have one additional data member. We have this data member of a tool pointer, and the identifier is called tool array. So we can imagine that each one of our characters in this particular game can have some array of tools. So let's say that we have character C1 and C2 again. And with character C1, we'll say that in his tool array, we'll imagine that this array is able to only hold 5 tools. So we have 5 elements here. But for right now, C1, Bob, only has an axe. Whereas over here with C2, Sally, she actually has 3 tools in her array. She has a potion, a crossbow, and a candle. So let's go back to our example where we were doing the assignment operation. So what happens now whenever we do this assignment of C2 to C1, all the data members, other than the case with the tool pointer, they all get assigned over. So all the things we see here in C2, Sally 8, 6, and 6, gets copied over here to C1, Sally 8, 6, and 6. But the problem is this particular tool pointer here is able to reference things out on the heap. So we can imagine creating a new tool array out on the heap, and whenever that occurs, what's actually getting copied here is exactly what's stored in that tool pointer, which is an address. So that address is being copied over. So we end up getting the address here in C2, whatever the address may be for the space out here on the heap, is getting copied here to C1. So it turns out that both C1 and C2 for the tool array, they're referencing the exact same array out here on the heap. And this is what we call a shallow copy. And so in order to avoid doing a shallow copy, this is where we need to have an overloaded assignment operator. So you can see in this particular case, if we made use of overloading the assignment operator for the character class, then we would end up with both C1 and C2 having their own respective copies of this array. And at that point in time, these characters could go forward and have different values for their tool array or different tools in their tool array. And this is what we would like to have happen. Let's look at another situation. So let's assume that we've written an overloaded assignment operator, but we end up with a situation like this, where we have C2, so the object C2, character C2 already exists, but now we're trying to create a new character called C3, and it doesn't exist, but we're going to initialize it with the values that currently exist in C2. So what's going to happen? Well, it turns out even if we had an overloaded assignment operator, it's not going to be invoked in this particular case because C3 wasn't already in existence. What's invoked is the copy constructor. And if we haven't written our own copy constructor, what will happen is C++ provides us a default copy constructor that performs another shallow copy. It doesn't perform a deep copy. So we just simply get that address that's being copied here from C2 to C3. And we end up sharing the exact same tool array out there on the heap. So again, overloaded assignment only invoked if the object already exists. So in this case, C3 didn't already exist, so we end up invoking the default copy constructor. So what we would need to do in this particular case is write a copy constructor. And we'll look at how to do that in our next video. All right, so let's take a look at what happens whenever we perform a delete operation. And we have a couple of scenarios here, but they really result in the same thing occurring. So we could have this particular thing here, this character C2, at least this portion that I'm moving my mouse over. This could exist either out on the stack or out on the heap. This particular tool array, we're saying that it's always going to exist out on the heap for this particular example. So the way that we had coded this up previously, whenever we had created character C2, we didn't use the keyword new. So that would be the case that this would be out on the stack. And so what would happen, as soon as we terminated whatever function this was created in, we'd have an automatic invocation of what's called the default destructor. And it would take care of all this business here, removing that from the stack. But this part here would still exist out on the heap. Even if we had created this out on the heap, so say that we'd use the keyword new, and then we would go in and make use of the keyword delete and delete C2. Well, even in that case, it would just only take care of this. It would still leave this part here out on the heap. So what we'd have in that particular situation, or either one of those situations, is garbage out on the heap. We would still have our tool array there existing out on the heap with no way to get to it. And we don't want that to occur. So what we need to do is write our own destructor for the character class. And this is going to go in and take care of anything that we may be referencing out there on the heap. All right, so in summary, when should we go about writing the overloaded assignment operator, the copy constructor, and the destructor? Well, it comes down to this. If we have a class in which we have members of that class that can reference heap space, then we should be writing all three of those: the overloaded assignment operator, the copy constructor, and the destructor. And in my next video, we'll go in and write a class in which we'll need to have all three of these and see what the syntax looks like.